Good day everyone. Today I'll take you through the fascinating world of set theory and its role in addressing fundamental problems in mathematics. Set theory emerged from the quest to solve deep issues related to infinity and the very nature of mathematics reasoning. By studying infinity and attempting to organize mathematical ideas, set theory became a revolutionary tool not just in mathematics but for understanding logic and structure. It's where the explorations of infinity began, pushing mathematics to redefine how we see the fundamentals of math. To give you an overview, this presentation will highlight how set theory revolutionized mathematics, how it tackled key issues like infinity and mathematical reasoning, and the framework it provides to address fundamental problems. Through this outline, we will explore how set theory shapes the mathematical world we know today. Now let's start with the basic. What is a set? A set is simply a collection of unique objects which we call elements. For example, a set of number would look like 1, 2, 3. Set can be finite like a set of the day in a week, or infinite like the set of all day numbers. Why is it important? Because set provide a framework to describe and analyze mathematical structure, making them a fundamental concept in math. Set theory isn't just about defining sets, it's also about setting rules to avoid confusion. These rules are called axioms, which are stated as assumed to be true without proof. An important axiom is an axiom of extensionality. It says that two sets are equal if they are contains the same elements. For example, if set A is equal to 1, 2, 3 and set B has 1, 2, 3, they are considered equal. These axioms make sure that our sets are defined, well-defined, and consistent when you use them. Let's talk about the person who started it all, George Cantor. George Cantor lived from 1845 to 1918. And made his mark while studying trigonometric series and infinity. He defined the set as a collection of distinct objects and introduced the concept of cardinality, which compressed the size of a set. His most breaking discovery was the theory of the different level of infinity. For example, the infinity of natural numbers is smaller than the infinity of real numbers. This insight completely changed how mathematicians thought about the infinite. Building on that, Cantor shows that not all infinite sets are the same size. Some sets like natural numbers are countable, meaning you can list them one by one, but others, like the set of real numbers, are uncountable because there are no way to list them all. This distinction revolutionized the rigor and formalism in mathematics, pushing the boundaries of how we define and work with infinity. However, set theory wasn't without its challenges. One major issue was Russell's paradox, discovered in 1901. It goes like this: if we create a set of all sets that do not contain themselves, does that set contains itself? If it does, then it shouldn't, and if it doesn't, then it should. This paradox exposed a serious flaw of naive set theory and raised questions about the consistency of mathematics. It was a wake-up call for mathematicians to rethink their approach. The solution to these challenges was axiomatic set theory, introduced by the mathematicians like David Hilbert. Hilbert proposed a formal system of axioms to define sets rigorously. These axioms provided clear rules that avoided contradictions like Russell paradox. This marked a shift from a naive set theory to more structured approach, ensuring mathematics could continue to develop on this stable foundation. Finally, let's talk about ZFC set theory, which is the foundations of modern mathematics. The Zermelo-Frankel axioms were developed to address fundamental problems, and later, the axioms of choice was added, creating ZFC. ZFC provide a consistent and reliable framework for mathematics. It's helped mathematicians define and analyze structures while avoiding contradictions, ensuring that the field continues to grow and evolve. And that's all for my part. My partner will continue our report. Thank you.
Hi everyone, I am Daisy Paneda and I am here to continue the discussion about set theory. Gödel's incompleteness theorems. Any sufficiently powerful system cannot be both complete and consistent. Implications: true statement exists that cannot be proven. A perfect mathematical foundation is impossible according to Gödel. Gödel proved that any powerful mathematical system will have true statement it can't be proved. It's impossible to have a perfect complete system. Founding the Arithmetic of Set by Richard Dedekind. Dedekind defined natural numbers recursively as set. Introduced Dedekind cuts a precise definition of real numbers. He also laid the groundwork of rigorous approach to numbers within set theory. Dedekind defined the natural numbers as a set, giving us a new way to understand their structure. He also came up with a precise definition of real numbers. Formalizing Logic for Set Theory by Gottlob Frege. Frege developed formal logic essential for set theories. Foundations attempted to derive arithmetic from logic, a monumental undertaking. His work, though flawed, was highly influential. Frege developed a formal logic which is essential for understanding set theory. He tried to build all of arithmetic from logic, an ambitious goal. Uncovering the paradox. Bertrand Russell. Russell discovers Russell's paradox, exposing inconsistencies in early set theory. This paradox highlighted the need for a more rigorous axiomatic approach. Co-authored of Principia Mathematica, aiming to rebuild mathematics on logic. Russell discovered a paradox in Frege systems, showing that early set theory had inconsistencies. This led to a need for a more rigorous approach to set theory. Axiomatic Set Theory by Ernest Zermelo. Zermelo developed a first axiomatic system for set theory. It is the Zermelo set theory. Provided a framework to avoid paradox like Russell. His work paved the way for a more consistent and robust set theory. Zermelo created the first axiomatic system for a set theory, a framework to avoid paradox. Completing the axiomatic. Abraham Frankel. Frankel extended Zermelo's axioms with the axioms of replacement. This crucial addition completed the most widely used axiomatic system, secured the Foundation for a modern set theory and its applications. Frankel completed Zermelo's system, adding a crucial atoms, creating ZFC or Zermelo-Frankel set theory with atoms of choice. Application across discipline. So, this is the application in different disciplines like mathematics, defining structure, provide theorems, like it is the fundamental theorem of algebra. In computer science, algorithms, data, structures. In philosophy, exploring infinity, foundations of mathematics. Set theory is used in many fields, including mathematics, computer science, and philosophy. Before we dive in, let's watch this video first for you to know more exciting about set theory.
Welcome to Discrete Mathematics. Let's start with set theory, which is a very fundamental notion in the entirety of mathematics. So what is a set? A set is a collection of objects called elements. And this is very vague because we can have a set about anything we want. And usually we talk about sets by drawing these little circles. So for instance, if I want a set of, let's say, the numbers 1, 2, and 3, I can draw a circle and I can put the numbers 1, 2, and 3 in there, and that is a set containing the numbers 1, 2, and 3. And we can write this formally in curly braces and writing all of the elements inside. So in this case, our set contains 1, 2, and 3, and we can give this a label and maybe call this A. So these are all different ways of representing the same thing. A is the set 1, 2, and 3, which looks like a circle containing elements 1, 2, and 3. Of course, this is just visual, and this notation in curly braces is called a list notation because you're listing them all. Now, sets can be finite or they can be infinite. So we can have a set A containing all the numbers between 1 and 9, or we could have the set of positive integers that go from 1 all the way up to infinity. And in this case, this is an infinite set. So these ... dots mean that there's an implied pattern that just goes on forever. So here, z plus, if we have 1, 2, 3, 4, and we put ... we mean that it goes 5, 6, 7, 8, 9, 10, so on and so forth. So those are really the fundamental notions of sets. Now there's some additional points to these sets, and that is that repeated elements are only listed once. So if we have a set A, B, A, C, B, A, even though A is repeated 3 times, we only write it once. B is repeated twice, we only write it once, and C is repeated once. So this set A, B, A, C, B, A is the same set as A, B, C, and they would both be drawn as circles with some element A, some element B, and some element C. In other words, we don't care about the amount of numbers of these things in there. We don't care if there's 3 A's, we don't care if there's 2 B's. We just want to know what's inside our circle. There's also no order in a set. And in a diagram, this is easy to see because there's no order in a circular diagram. But essentially, the set 3, 2, 1 is the same thing as the set 1, 2, 3. And that's also the same thing as the set 2, 1, 3, so on and so forth. There's no order to these sets. So those are two pretty important parts. Usually on an exam, you might be given a set that has repeated elements, and they might ask you, how big is this set? How many things are in it? And if you're not sure about repeated elements, then you might get the wrong answer. There's a few common sets that we should talk about. One of them is the natural numbers. The first time I made this video, some controversy. And there's still some controversy. But there's 2 ways to do the natural numbers. One of them is to start with 0, do 1, 2, 3, all the way up forever and ever. Another group of mathematicians starts the natural numbers with 1, 2, 3, so on and so forth. I'm going to refer to the natural numbers, starting with 1, as the positive integers. And when I talk about natural numbers anywhere else, I will usually mean including 0, but I may be more specific about it, so I will specify whether it includes 0 or not. But typically with 1, 2, 3, so on and so forth, I'll use z plus. The integers are a set of numbers which are either positive or negative, and they're whole numbers. So all the way from negative infinity, -2, -1, 0, 1, 2, all the way to positive infinity. So that is z. That's a very important notion, which we use a lot in discrete math. And then rational numbers. Oh, these are kind of hard to list. So I'm going to cheat a little bit for now, and I'm going to say, well, we have like 1 over 1, 1 over 2, 1 over 3, 2 over 3, so on and so forth. And in a few slides, we'll figure out a better way to write this. So, of course, rational numbers are any numbers you can write as a fraction. So, elements and cardinality. Now we know what sets are. Now we know some additional pointers about sets. We know some common sets. But we want to be able to talk about the things in those sets and how big those sets are. So I have C, and I have a set containing yellow, blue, and red. So these are the primary colors. In fact, sets don't have to be all mathematics. They can be words too and have meaning in the real world. So I want to say something like yellow is an element of C. And this means that yellow is inside of our set C. Now, how do we write this? Well, we have an element yellow, and we want to say it's part of a set C. So in order to write this in notation, we use this epsilon. So yellow is in the set C. What about saying green is not in the set C? So I want to say green is not in here. In fact, we don't see it in the set C. So what do we do to say green is not in C? Well, we use the set membership symbol, and we just put a line through it to mean green is not in our set C. How do we talk about the size of this? How do we say the size of C is 3, which means the amount of things in C is 3. There are 3 different elements in C. Well, we just draw these absolute value bars around it. So we say that the absolute value, or the size of C, is equal to 3. And that's just that the cardinality of C is 3. So now we can talk about whether things are in our sets and how many things are in our sets. Now there's one particularly interesting set that contains nothing in it. This is called the empty set, and this is written with this symbol. And if I wanted to write it in the set notation with curly braces, it would look like this. It has a left curly brace, a right curly brace, and then there's nothing inside of it because it's empty. So what's the size of this set? Well, there's nothing in it. So the size of it is 0. And there's only one set that has a size of 0, and that is the empty set. So here's a question. And I'm throwing this right at you right away because this trips people up all the time. What is the size of the set containing the empty set? So I'm asking, if I have a set containing the empty set, what's the size of that set? Well, this empty set is an element of the larger set. So the size of the set containing the empty set is 1 because this set itself, this big set, has one element. It has an empty set as an element. So sets can have sets as elements. We'll see another example later, but typically I like to look where the commas are. So if there's like a big set, then a comma, then another big set, and that's all that's in the set, then there'd be 2 elements. In this case, we have these empty braces, but there's something inside of it. So therefore, there's an element in that set. This is different, of course, than the size of the set containing nothing. This would be 0. So we can see the contrast between these 2 sets. This is the empty set on the right, while this is a set containing the empty set on the left. The left one has a size of 1, the right one has a size of 0, and we can see the differences visually. Okay, so that's the empty set. There'll be more questions about the empty set when we get to the subset video, so more tricky stuff will happen there. The next thing we should talk about is set builder notation. So before I introduced the rational numbers, and I said, oh, it's 1 over 1, 1 over 2, 1 over 3, 2 over 3, so on and so forth, there's got to be a better way of representing this entire set. And this is set builder notation, or we can call it maybe predicate notation, where we define elements as variables. So for instance, I can say this is the set containing elements that are of the form m over n, such that, so this straight bar means such that, and now I'm going to give a rule. So the left is like the form that it takes, and on the right side, we're going to give it a rule. We're going to say that m and n have to be integers, and also n has to not be 0, so that way we're not dividing by 0. And this expresses the entire set of rational numbers. I'm saying, look, take any two integers, m and n, we can put m on top of n, and as long as n isn't 0, it's going to be in that set. So I'll do another example with even integers. So we can write all the way to negative infinity, negative 4, negative 2, 0, 2, and 4, so on and so forth to infinity. Or we could do this in set builder notation. So we could say that this is the set of 2n such that n is an integer. So what this means is we take an integer n, so let's say we take 1, then in our set we add 2 times that integer, so 2 times 1, so we add 2. Let's say we take 2, then we take 2 times 2 and put in our set 4. Let's say we take negative 1, then we take negative 1 times 2, and then we get negative 2 in our set as well. And this just goes on forever. So for every n that is an integer, we add 2n to our set. And that gives us the set of even integers. So here's a more linguistic example, so something we can apply in the real world to see how this notation works. I have a desk. And on this desk, I have a drink, I have a laptop, and I have a microphone. And there's some other things on my desk that I could list, but let's just say my desk only has these 3 things. Now, this is one way I can talk about things. I can say I got this drink, this laptop, and this microphone on my desk. Or I could write this in set builder notation if I might have a lot more things, or maybe I want to be vague, or maybe I'm not entirely sure what's on my desk, but I know there's things on my desk. So I could rewrite this as the set of x. So this is a variable x. And what's the condition for x? X is on my desk. Yeah, so this is kind of cheating, right? But they're the same sets. So the first one I'm listing all these items individually. The second one I'm saying, look, it's the set of variables x, and whatever x is, it just happens to be on my desk. So everything that's on my desk, it's just going to shove it in as x, and it's going to build a set with it. So that's the set builder notation. And of course, mathematically, we do this very formally with, of course, numbers and formulas and notation. While, of course, if you do a linguistics example with words, it's much more wordy, it's much more flexible, much more floaty, but they both convey the same meaning. So if you didn't quite understand the mathematics example, then hopefully you'll be able to translate this desk example back into the mathematics after, while maybe understanding this at a more fundamental level. So here I have some exercises. And these all refer to the first 2 refer to the set D, and the third one is completely different. Try them yourself, and if not, well, I'll give you the answers now. So list the elements of D. D is the set of x in positive integers such that x is less than 6. So I'm going to take all x less than 6 and add them to the set if it's a positive integer. So this means that I can have 1, because 1 is a positive integer and it's less than 6. Let's do this in a different color. 2, 3, 4, and 5. Can I add 6? I can't add 6 because x is not less than 6. Can I add 0? Well, I can't add 0 because I specifically want the x's that are in positive integers, and 0 is not a positive integer. Okay, what's the cardinality of D then? Well, this is easier because I've already written out all the elements in my set. So I see there's 5 things there. So I can say the cardinality of D is equal to 5 because it contains the numbers 1, 2, 3, 4, and 5. Now here's another question, and this is what I alluded to before. What is the cardinality of the set containing the empty set and the set AB? Okay, so how many elements are in the set? And when we look at sets, it's kind of like looking into a box and saying, well, what can I see? I see an empty set, and I see another set. So really what I see inside this box, if I were to draw this out, is a box containing nothing and a box containing A and B. So the stuff inside of these boxes, essentially with a cardinality question, these things are invisible. We can't see what's going on. So the question is, how many things do we see inside that set? What is the size? How many elements are in that set, that big box? And the answer to this is 2. And this is why I said look at the commas here. So we have an empty set, which is the first thing. Then we have a comma. Then we have this other entire set. So there's 2 things we can see. Now, how does this differ from, let's say, if we have a set containing the empty set, the set containing A, and then the set containing B? Well, this is different, of course. So in this example, if I were to draw this, we have a box containing nothing in it. We have a box with A in it, and then we have another box with B in it. So how many elements do we see? Well, we can't see inside these boxes, but if we just open our box and take a look, we'll see 3 other boxes. So in other words, the size of this would be 3. One more example. Let's say we took away one of these. So now I have something that looks like this. I have the empty set, I have the element A, and I have a set containing B. Once again, there are 3 elements that we can see. We can see this box containing something, we can see the element A, and then we can see this box containing something else, which happens to be B. So once again, this cardinality is equal to 3. So that is it for the Introduction to Set Theory video. If you have any questions, please leave them in the comments below and I will do my best to answer them.
Okay, we are going now to the last part, which is the conclusion. To sum up everything that we said, set theory, a groundbreaking approach to understanding infinity and mathematical structure. Challenges like Russell paradox and Gödel's theorems highlighted its limitation. Axiomatic set theory, which is the ZFC, remains central. 2. Mathematics. The research for foundation clarity continues to inspire advancement. Set theory is a powerful tool for understanding mathematics, but it has limits. The search for a perfect mathematical foundation continues. And that's all. Thank you.